Welcome everyone. During this lecture we'll introduce the concepts of work and energy, and then we'll demonstrate the application of these concepts through two examples. Let's begin by defining work. Work is a measure proportional to the amount of effort expended while causing an object's displacement through the application of a force. Now there are two quantities that really stand out within this definition, and they are displacement and force. And so, in order to do work, two things must occur. One, a force must be applied. And secondly, that force must cause or resist a displacement. We will now develop the equation for work. In order to accomplish this, we will consider a horizontal surface that looks like this. Let's now represent a block on that surface that has a mass of m, and now let's push that block across the surface with a horizontal force represented by F. We will assume that this force causes the block to displace, and so the block ends up at this location sometime later, and as a result that block has a displacement which we can represent by delta x. So we're satisfying the two conditions for work. Let's take a look. We are applying a force, and that force is causing the object to displace. So we are doing work within this example. The question is, what is the equation for work? Work is defined as simply the product of the force times the resulting displacement. And this equation is only valid when the force that's being applied is parallel to the displacement. And that's what we have under these circumstances. This force is parallel to the displacement. I will indicate that requirement by putting two parallel lines next to this force. And so again, whenever the force is parallel, this is the work equation. The question now is, what happens when the force is not parallel but still causes an object to displace? When you think about it, Anytime you're pulling a wagon or pushing a shopping cart, your arms are not parallel to the ground, but you are in fact causing a displacement. So the question is, how much work are you doing? Let's explore that question. So once again, in this example, we'll lay out a horizontal surface. There's our block that has a mass of m. We will push this block with a force that looks like this, and notice that this force is not parallel to the displacement. Despite this, the object will end up at this location at some time in the future, and therefore the object has undergone a certain displacement, which is noted by delta x. The question is, how much work was performed? Well, in order to answer that question, we must first note the angle between delta x, in other words the horizon, versus the force that we're applying. And let's label that angle as theta. Next, what we will do is draw the x and y components of this force. And so this force has a tendency toward pushing the object to the right, and so the x component is directed horizontally to the right. We'll label it as F sub x. And it also has a tendency of pushing the object against the surface in a downward direction. We'll represent that component as F sub y. Now, one of these components is actually causing the displacement, and the other one is not. Can you tell which is which? Well, clearly F sub y is only squeezing the block against the surface. It's not causing it to travel to the right. On the other hand, F sub x is directed along the x-axis, and F sub x therefore is causing the displacement. And so in our consideration, we will ignore F sub y and consider that F sub x is the only component that's performing the work. And therefore we can write the work equation as F sub x times delta x. Now, how is F sub x related to F? In order to answer that question, let's just construct a simple triangle like this. Here is F. This is F sub x, and this leg of the triangle is F sub y. Here's our angle, that's theta, and of course F sub x is the adjacent side, right? The adjacent side is the side that borders the angle, and therefore it is related to the cosine function. From trigonometry, we can state that F sub x just equals F times the cosine of the angle. And so let's bring that result into our work equation. If we substitute the right-hand side into the work equation becomes F cosine theta times delta x, which we prefer to write as F delta x cosine theta. And that is the general equation for work. Let's also emphasize the fact that theta is the angle between the force vector and the displacement vector. In other words, theta is not the angle with respect to the positive x-axis necessarily. Now it's the angle between the force vector and the delta x vector. And it's important that when we are calculating theta, we draw the delta x vector and the force vector so that their tails are tied together. This is what I mean. Whenever we're trying to determine theta, it's important to draw delta x, which looks like this in this case, and then draw our force, but make it so that the tails are tied together. In other words, vectors have a tail and a tip. In this case, we're tying the tails together. We're preserving the orientation of the force and the displacement. And once we have them tied tail to tail like this, theta is just the angle between them. We will now introduce the units for work. Starting with a consideration of the equation that we just derived. Work equals force times displacement times the cosine of the angle between the force and displacement vectors. Force in the international system has units of newtons, and displacement is described by meters. The cosine of an angle is unitless, and so the work unit would be the Newton meter. However, the scientific community refers to a Newton meter as a joule. So 1 Newton meter is referred to as 1 joule in recognition of a 19th century British physicist named James Prescott Joule. The joule, of course, is an international system unit, so we'll note that as an SI unit. What about the British system? Well, in the British system, again, work still equals force times displacement times the cosine of the angle between the two. However, the unit for force is the pound, and the unit for displacement in British is the foot, and that is the unit for work. It's the foot-pound. Let's summarize these results. So the units for work are joules in the SI system, and the foot-pound, or the pound-foot, in the British system. I'd like for you now to consider the following question. Would you accept a job that pays 10 cents per joule? Take a moment to think about that, and then we'll analyze whether we should take this job or whether we should reject it. Well, let's explore how much work is involved in the production of a joule. As we noted earlier, 1 joule is the product of a Newton and a meter, and so we would have to apply a force of 1 Newton and cause a displacement of 1 meter. We can do this. Let's imagine a textbook in front of us, and let's also imagine that we're sitting at a table that's 1 meter in length. Applying a force of 1 Newton, again, is only a matter of applying 1/4 pound of push. That's a very, very small amount of force, and anybody can do that. So let's imagine that we're pushing our textbook with 1/4 pound of push and causing the textbook to travel across the length of the table, which has a length of 1 meter. I think that's a pretty simple thing to do, and so performing 1 joule of work does not amount to a whole lot of effort. I also believe that we can do this in 1 second, right? We can push the textbook end to end across that table in 1 second, and so we can perform 1 joule of work in 1 second, and this job would pay us 10 cents for doing that. That amounts to 10 cents per second. And so in 1 minute, if we push the textbook back and forth across the table 60 times, we will earn $6 per minute, which translates into $360 per hour. I think we have our answer. I would definitely take this job. Let's consider another example. In this example, a student pushes against a wall with a force of 100 newtons for a period of 3 hours. Let's determine the amount of work performed by the student. Well, the work equation looks like this. Work equals force times displacement times the cosine of the angle between these two. And by the way, notice that there's no reference to time in the work equation. Now, the student applies a force of 100. The student is pushing a wall, and I think it's safe to assume that the wall is not undergoing a displacement. The wall is going to be in static equilibrium, right? Unless the student, of course, is Superman or Superwoman. We'll assume that that is not the case, and therefore the displacement is 0, and the work, according to this equation, is 0. So there's a big difference between our consideration of what constitutes work versus the physics definition of work. According to the definition of physics, if you had a job requiring that you push a wall with 100 newtons of force for 3 hours per day, you're not performing any work whatsoever. And so the work under these circumstances equals 0. By the way, from this point forward, work will be abbreviated with a W. So the symbol for work, unfortunately, is the same as the symbol for weight, and it's important that we don't confuse the two. So whenever there's an opportunity to distinguish between them, I will take that opportunity. Unfortunately, like I said, though, the symbol for work is the same as it is for weight. We use the same letter, which is W. Now that we understand the definition of work, energy is relatively simple to define. Energy is just a measure of the capacity to do work. And the units for energy are the same as those for work, namely joules and pound-feet. So for example, when someone says they have a lot of energy, what does that mean? Simply translated, it means that that person can do a lot of work. Where did that person gain the capacity to do that work? Well, the answer is through the consumption of food. Human beings and animals gain an ability to do work. In other words, they gain energy by consuming food. Now, a gallon of gasoline also is considered to have a lot of energy. What does that mean? That means if we place a gallon of gasoline within a combustion engine, that engine will be able to also perform a lot of work. And so simply put, energy is just a measure of the capacity to do work. We will now introduce two applications that involve the principles of work and energy. In the first application, a student pulls a 65-kilogram wagon over a distance of 25 meters along a level frictionless floor as shown below. If the tension in the handle equals 45 newtons, we will start by drawing a free body diagram for the wagon, and then we'll also solve the remainder of the problem. So let's begin by drawing a free body diagram on the wagon. And so here's our wagon. It has a mass of 65 kilograms. And because of that, it also has a weight. So let's represent the weight like this. And of course, the weight equals mass times gravitational acceleration. The mass in this case is 65 kilograms. Gravitational acceleration equals 9.8. And if we multiply those two together, the result is 637 newtons. The wagon interacts with the surface as well, and the floor is exerting two normal forces, as one on the rear wheel, one on the front wheel. We'll just represent both those forces as one aggregate normal force. So those forces will be represented by this vector right here. Of course, the normal force is labeled as N. We also note that the student is pulling along this handle with a tension equaling 45 newtons. We can represent that with this force. We'll label it as T because it is a tension. We'll also note that that tension is directed at 30 degrees with respect to the horizontal. And anytime we have a force that's not aligned with X and Y, what I like to do is to resolve the force into its components because it makes the analysis a little easier going forward. So let's proceed with that. What I'll do is I'll construct a Cartesian coordinate system right here. Let's transfer that tension over here. This is the 30-degree angle. And we would now like to illustrate Tx and Ty. Of course, the x component would look like this. We can call that T sub x. And the y component for that tension would look like that. Now the tension equals 45 newtons. And what I'd like to do now is to find the values for T sub x and T sub y. Of course, from trigonometry, T sub x is the adjacent side, and so it would equal the tension times the cosine of 30 degrees. The tension equals 45. And from that, the value for T sub x ends up equaling 38.97 newtons. Likewise, for T sub y, we can use the T times sine 30 relationship. That equals 45 times the sine of 30. And the result for T sub y is 22.5 newtons. We'll just file that away for now and then apply it as we pursue the remainder of the problem. In part B of this problem, we would like to determine the normal force between the wagon and the ground. Of course, the normal force is represented by the letter N, and to find the normal force, we will just apply Newton's second law, of course, in the y direction because the normal is directed along the y-axis. And so according to Newton's second law, the sum of the forces will either equal 0 or ma or minus ma, and the FBD will help us to make that determination. According to our free body diagram, there is no acceleration in the y direction. And so we will choose 0. So the guiding equation looks like this. Sum of the forces in the y equals 0. The question now is, how many forces are directed along the y-axis? Let's take a look. Here's our free body diagram, and we notice that certainly the normal is aligned with the y-axis, the weight is aligned with the y-axis, and also the y component of the tension. This guy right here, T sub y, is also aligned with the y-axis. So there are three forces. By the way, while we're here, let's also include the fact that there may be an acceleration in the x direction. We won't rely on it, but for the sake of consistency, let's include it within our diagram. So there's the acceleration, and now we have a complete free body diagram which looks like the free body diagrams that we constructed earlier. Okay, so back to the second law analysis. We have three forces that we'll be considering, and so we'll extend three fingers from the summation. The normal goes in as a positive, the weight is directed downward, so it goes in as a negative, and T sub y goes in as a positive, because of course it's directed upwards. The weight has a value of 637. We calculated T sub y as, let's take a look, T sub y was 22.5, so we'll add it in. And what we'll do now is we'll transfer both of these values to the other side. And so that results in positive 637 minus 22.5, and if we enter those values into the calculator, we get a value of 614.5 newtons. And so here's an example where the normal does not equal the weight. And that's because we had a tension that was oriented in two dimensions. It had an x component as well as a y component. So the takeaway from this is the normal does not necessarily equal the weight for all problems. There's some times where the normal and the weight have two different values. In part C, we want to determine the work done on the wagon by the student. We'll refer to that as the work done by the student. And we know from the work equation that the work done by the student simply equals the force that the student applies times the resulting displacement times the cosine of the angle between the force and the displacement. Now the force that the student is applying is called the tension in our problem, right? And also the angle between that tension and the displacement could be noted in this diagram. So the tension looks like this. The displacement is directed horizontally, and therefore the angle between the tension and the displacement equals 30 degrees. And of course that's the value that we'll be using in the equation. So as a result, the work done by the student equals the tension, and by the way, let's take a look at the tension's value. The tension equals 45 newtons. So we have 45, the displacement equal 25 meters, and the angle between them is 30 degrees. So if we multiply these three together, we obtain a result of 974.3 joules are the units for work. In part D, we need to find the work done by the normal. Okay, once again, the work equation equals the force of the normal times the displacement times the cosine of the angle between the normal and the displacement. Now, the force that the normal produces is called N. We're referring to that as N. And let's also look at the relationship between the normal force and the displacement. Now, in our free body diagram, the normal force is directed upward, and the displacement is directed to the right. And the angle between them is 90 degrees. Let's see how that affects the result. So if we proceed, this becomes the normal force, and we calculated that earlier to be 614.5. The displacement is 25 meters. However, the angle is 90 degrees. And the cosine of 90 is 0, and therefore the work done by the normal is equal to 0. And that's because the normal does not contribute at all to the displacement of the wagon. If the force is pushing directly upward, it has no influence over the horizontal, the left to right motion. And so the work done by the normal equals 0. Finally, we want to determine the work done by gravity in part E. Well, here's the work equation. The work done by gravity would equal the force of gravity times the displacement times the cosine of the angle between the force and the displacement. Now, we refer to the force of gravity, of course, as W. So the force of gravity is just the weight, and I don't want to confuse W for weight versus W representing work, so I'll spell out the word weight, right? The force of gravity is just equal to weight. And the weight of the object we calculated earlier is 637 newtons. The displacement is 25. The question now is, what is the angle between the weight and the displacement? Let's draw them tail to tail. So the weight is directed downward like this, and the displacement is directed to the right, and the angle between them, as you can see, is a 90-degree angle. And so once again we have the cosine of 90, and the cosine of 90 is 0, and therefore the work done by gravity also equals 0. Let's introduce another application. In this example, a student expends 6,000 joules of mechanical energy while retracting a 20-kilogram bucket from a well at constant speed, as shown below. Let's take a look at the diagram. You'll note that there's a bucket at the bottom of a well. The depth of the well is specified as H. You can see that the student is pulling on a string that's attached to the bucket, and as a result of that pull, the bucket is raised a distance of H at constant speed. Let's draw a free body diagram for the bucket. So here's our bucket. The mass of the bucket equals 20 kilograms. And as a result, the bucket has weight. So the weight can be represented by this arrow. It's always directed downwards. Weight equals mass times gravitational acceleration as always. In this case we have 20 times 9.8, which results in a weight of 196 newtons. The bucket's also attached to a string which exerts a tension that's directed upward. So there's our tension. There's no normal force because We're considering the problem as beginning just at the moment when the bucket leaves the bottom of the well, and so there's no contact with these surfaces, and therefore there's no normal force. Let's also note that in the body of the problem, the bucket is traveling at constant speed. That means there's no acceleration. Let's indicate that within our free body diagram. So we'll draw an acceleration vector like that, but we'll at the same time indicate that the value equals 0, and that's because of the words constant speed. In part B, we would like to determine the tension in the rope. And we're going to apply Newton's second law in order to determine that tension. So according to Newton's second law, if we add the forces in the y direction, they will either equal 0 ma or minus ma. In our free body diagram, we can note that the acceleration equals 0, and that's what we will choose for the right-hand side. So the governing equation becomes sum of the forces in the y equals 0. And we'll also note that there are two forces acting in the y direction, namely the tension and the weight. The tension will be entered as a positive variable and the weight will be entered as a negative. And so we'll extend two fingers from the summation. Here's our tension, here's our weight. Together, they equal 0. Now, of course, the weight has a value of 196 newtons. We'll transfer that to the other side, and therefore the tension simply equals 196 newtons. So when there's no acceleration, the tension, in this case, simply equals the weight. In part C, we would like to determine the depth of the well, which we've labeled as H in our diagram. And in order to find H, we will apply the work equation. So earlier we wrote that work equals force times displacement times the cosine of the angle between the force and the displacement, and we're going to customize this equation for the work done by the student because we know the amount of work that the student has applied to the bucket. Specifically, if the student expends 6,000 joules of mechanical energy, that energy is transformed into the work done on the bucket. So we'll identify the work as the work done by the student, which is connected to the force applied by the student, times the displacement of the bucket, times the cosine of the angle between the two. Now, the work done by the student was given as 6,000 joules. The force applied by the student actually equals the tension in the rope. And the tension in the rope we just calculated right here as 196. The displacement is unknown, so we will just call that H. Right? The displacement of the bucket will equal the depth of the well. So we can enter that over here. And now, as far as the angle between them, well, let's note that the tension at the location of the bucket is directed upwards, and the displacement is also directed upwards. So what is the angle between them? Well, the angle between any pair of parallel vectors is 0 degrees. Now I realize that the two vectors are directed straight up, which is normally a 90-degree angle, but I'm not interested in their orientation. We're interested in the angle between them. And once again, parallel vectors have an angle of 0 degrees between them. So we'll enter that as cosine of 0. Now the cosine of 0 equals 1, so this equation becomes 6,000 equals 196 times h. If we just divide both sides by 196, we can get the depth of the well. That depth equals 30.61 meters. In the last part of the problem, we would like to determine the work done by gravity. Well, the equation is, once again, W equals F delta X cosine theta. We're interested in the work done by gravity, which is connected to the force of gravity, times the displacement times the cosine of the angle. Now, the force of gravity just is simply the weight, right? Gravity creates the weight upon an object, and I'll spell it out as weight so we don't confuse it with work. So this is the work done by gravity. This is the weight that is produced by the gravitational attraction between the Earth and the object. And so the weight we calculated earlier as 196 newtons. Let's bring that into the work equation. The displacement we just calculated as 30.61. And as far as the angle, well, let's draw the weight vector, which looks like this. And the displacement vector is directed upwards. And so when two vectors are pointing in opposite direction, the angle between them is this one right here, which happens to equal 180 degrees. And so we will include the 180 degrees within our calculation. So the work done by gravity equals negative 6,000 joules. And that's not a coincidence. By the way, if you noticed that the work done by gravity is the negative of the work done by the student, that is not a coincidence. That is actually necessary whenever an object is not experiencing a change in its speed. And so that is the case. In this problem, the bucket had a constant velocity. The speed was not changing, and that means that if we add up all the work done on this object, that work should add up to 0. And again, the student's work equals 6,000 joules, the work of gravity equals negative 6,000 joules, and if we add them together, we get a net work of 0. And we will explore the implication of changes in velocity in just a little bit when we develop something called the work energy theorem. And that concludes this lecture.